I hope you can see on the screen the.
Yes, ma'am.
Okay. You probably know about differential equations when we had taken time as a continuous variable, but we come to difference equation. Today we discuss the first order difference equation. Now, to begin with, we must learn what we mean by difference equation. When time is a discrete variable, the variable t is allowed to take integer values only. The concept of derivative will no longer be appropriate. The pattern of change of the variable y must be described by the differences rather than by derivatives or differentials of yt. Now, when time is discrete, the value of variable y will change only when variable t changes from one integer value to the next. For example, when t changes from t is equal to 1 to t is equal to 2, meanwhile, nothing is supposed to happen to y. It becomes more convenient to interpret the values of t referring to periods rather than points of time. Uh, T is equal to 1 denotes period 1, t is equal to 2 denotes period 2, and so on and so forth. We simply regard y as having one unique value in each time period. The discrete time version of economic dynamics is often referred to as period analysis. However, period is being chosen here or used here not in the calendar sense, but in the analytical sense. You need to concentrate a bit more to understand this. Uh, Here we are trying to say that period is being used in an analytical sense, not in the calendar sense. What does it mean? A period may involve one extent of calendar time in a particular economic model, but an altogether different one in another. Even in the same model, each successive period should not necessarily be construed as meaning equal calendar time. Um, Now, what do we mean by this analytical sense? So, in analytical sense, a period is merely a length of time that elapses before the variable y undergoes a change. It is not like the 13th of July is different from 12th of July. No, it is just a period is just length of time that elapses before the variable y undergoes a change. Now, a dynamic problem is to find a time path from some given pattern of change of a variable y over time. The pattern of change is represented by the difference quotient delta y by delta t, which is the discrete counterpart of dy dt, which you already know. We are comparing the values of y in two consecutive periods. That means delta t is equal to 1 For this reason, the difference quotient delta y by delta t can be simplified to the expression delta y. Because the denominator delta t is said to be equal to 1, this delta y by delta t becomes only delta y. And this is called the first difference of y. The symbol delta constitutes the discrete time counterpart of the operator symbol d dt. I hope it's clear up till here.
Yes,
Please
ma'am.
respond. It's clear up till here?
Yes, ma'am.
Okay. Now, the expression delta y can take various values depending on which two consecutive time periods we are considering in difference taking or differencing. To avoid ambiguity, let us add a time subscript to y and define the first difference more specifically, like delta yt is equal to delta yt plus 1 minus delta yt, where delta yt means the value of y in the tth period, and delta yt plus 1 is the value of y immediately following the tth period. With this symbol, we may describe the pattern of change of y by an equation like delta yt is equal to 2 or delta yt is equal to minus 0.1 yt. Now, equations of this type are called difference equations. Even though difference equations derive their names from difference expressions such as delta yt, there are alternate equivalent forms of such equation. For example, delta yt is equal to 2 can be written as yt plus 1 minus yt is equal to 2, or it can be written as yt plus 1 is equal to yt plus 2. Now coming to the next equation, that is 3, this can be written in a number of ways, that is yt plus 1 minus 0.9 yt is equal to 0, or delta yt is equal to yt plus 1 minus yt is equal to 0.1 yt. Now, if we take this 0.1 yt here, we will get this equation. It is important to note that the choice of time subscripts in a difference equation is somewhat arbitrary. For example, without any change in meaning, yt plus 1 minus yt equal to 2 can be written as yt minus 1 is equal to 2. That is, the difference in the value of y into consecutive period is equal to 2. So this and this are similar. So here t minus 1 refers to the period which immediately precedes the tth period, or it can be written as yt plus 2 minus yt plus 1 is equal to 2. I hope this is pretty simple in understanding. We are just taking the difference in the value of y in two consecutive periods, be it t plus 1 or t or t minus 1 or t plus 2 or and t plus 1. Now we come to the solution of difference equation. Before coming to the solution, we have to define a difference equation properly. So difference equations can either be linear or non-linear, homogeneous or non-homogeneous, and first order or higher order. Now we have uh, enumerated three differences between difference equations. So let us take up the meaning of each one by one. It is linear when no y term of any period is raised to the second or higher power or is multiplied by y term of another period. That means we will not have yt squared or yt plus 1 squared term, or we will not have yt plus 1 into yt term in our equation. If we do not have these, our difference equation is linear. Now, difference equation can be homogeneous as well as non-homogeneous. Now, what is non-homogeneous? When we have in a, a difference equation is non-homogeneous when the right-hand side, where we do not have any y term, is non-zero. So, right hand side non-zero means non-homogeneous. If right hand side is zero, we have a homogeneous difference equation. Now, coming to the order of a difference equation. First order difference equation exists when only first difference or one period lag exists. Second order difference equation involves a two period lag and thus entails yt plus 2, yt plus 1 and yt. That is, we have taking two period lag here. When we are talking in terms of first order, which we were showing in our previous examples, there was just one period lag. But for higher order difference equations, we have, for second order, for example, we have two period lag, and as the number of lags increase, the order of the difference equation is also supposed to increase. Now, the solution of a difference equation is the time path. This time path is a function of t. That is a formula defining the values of y in every time period, which is consistent with the given difference equation as well as with its initial conditions. It must not contain any difference expressions such as delta yt or delta yt minus 1 minus yt. Suppose we are seeking the solution of yt plus 1 plus ayt is equal to c. Now, for the solution, the first thing we have to write in our answer scripts is about the nature of the difference equation. That is, it is a first order because there is only the first difference, that is yt plus 1 and yt. Linear because no yt term is raised to a higher power or yt plus 1 is multiplied into yt. And non-homogeneous because the right hand side, which does not have any say y term, is non-zero. So first sentence to be written in solving a difference equation is about its order, whether it is linear or non-linear, homogeneous or non-homogeneous. The next point is that the general solution consists of two parts, yp, the particular integral, and yc, the complementary function. Now, the complementary function is a general solution of the reduced form. That is, we make the right-hand side which does not have any y term equal to 0, and we get the equation in its reduced form. So yt plus 1 plus ayt is equal to 0. Now, the particular integral yp represents the intertemporal equilibrium, whereas yc represents the deviations of the time path from the equilibrium. Now, the sum of yc and yp constitutes the general solution because of the presence of the arbitrary constant. Then we have to definitize the solution with initial conditions. Now we begin with our solution. So initially we write about the nature of the difference equation. Second part is that we say that the general solution consists of two parts, yc plus yp. Then we move on to the actual solution. For the complementary function yc, let the trial solution be yt equal to ab to the power t, with ab to the power t not equal to 0. If it is equal to 0, yt will turn out to be a horizontal straight line lying on the t-axis. So, next step is to write for the complementary function yc, let the trial solution be yt is equal to ab to the power t. The homogeneous equation will become a b to the power t plus 1 plus a b to the power t is equal to 0. We take a b to the power t common, and we have in the brackets b plus a is equal to 0. We have assumed that ab to the power t is not equal to 0. That means b plus a is equal to 0. So b is equal to minus a. So we substitute this value of b in our complementary function to get the complementary function as yc is equal to a into minus a to the power t. Now we come to the particular integral. For particular integral, we try yt is equal to k, where k is a constant. We substitute for yt plus 1 as k and yt as k, and get k into 1 plus a is equal to c, which gives us the value of k equal to c by 1 plus a. This will be defined only when a is not equal to minus 1. If a becomes minus 1, we have 0 in the denominator, so k becomes undefined. Now, what will we take as trial solution if a is equal to minus 1? We will take it to be kt. So we substitute kt in the equation to get k, the value of k as c, because a is equal to minus 1 and these two terms get cancelled out. So we have k is equal to c. So yp in this case is ct. When a is equal to 1, minus 1, yp is equal to ct. This shows a moving equilibrium. Previously, uh, when a was not equal to minus 1, we had a as a constant, so we got a stationary equilibrium, but here we have a moving equilibrium. Now we come to the next step. What is the next step? We add yc and yp and get the general solution in one of the two forms. That is, yt is equal to a into minus a to the power t plus c by 1 plus a, where a is not equal to minus 1 and yt is equal to a plus ct, where a is equal to minus 1. Neither of these two equations are completely determinate in view of the arbitrary constant a. Now, to eliminate this arbitrary constant, we resort to the initial condition that yt is equal to y0 when t is equal to 0. Let t is equal to 0 in equation 4 and obtain a as y minus c by 1 plus a. Consequently, the definite version of the general solution becomes yt is equal to y0 minus c by 1 plus a into minus a to the power t plus c by 1 plus a. What we had said, this is the stationary equilibrium. Right. Now, letting t equal to 0 in the case where a is equal to small a is equal to minus 1, we get y0 is equal to a. Hence, our solution becomes yt is equal to y0 plus ct. Now, the validity of the solution may be checked by the following two steps. That is, by letting t is equal to 0 in the solution and the equation reduces to the identity y0 is equal to y0, signifying the satisfaction of the initial conditions, or by substituting yt in the formula. Now we take a few examples. It would have been better if you could solve it now, but since it is not possible in this online method, you will solve it and send it to me later. So solve yt plus 1 minus 5yt is equal to 1, y0 is equal to 7 by 4. This is our difference equation. So first thing we have to write is that it is a first order linear non-homogeneous difference equation. Next sentence, the general solution ys is equal to yc plus yp, where yc is the complementary function and yp is the particular integral. For yc, we take the equation in its reduced form, that is yt plus 1 minus 5yt is equal to 0. We take a trial solution, yt is equal to ab to the power t, where ab to the power t is not equal to 0. So we substitute for yt in this equation to get the value of b to be equal to 5. So our complementary function becomes a 5 to the power t. Now for particular integral, let the trial solution be yt is equal to k, and we get the value of k to be minus 1/4. So we substitute the value of yp here to get the solution in its general form. We definitize this solution with our initial condition, which says that y0 is equal to 7/4, which gives us a value of 2 to a. We substitute the value for a in this equation to get yt equal to 2 into 5 to the power t minus 1/4. So this is the solution of our first order linear non-homogeneous difference equation. Now we take another example. What is it? It's yt plus 1 plus 3yt is equal to 4, and the initial condition is given as y0 is equal to 4. So the general solution consists of two parts, yc plus yp. Before that, you have to write that this is a first order linear non-homogeneous difference equation. Then the general solution consists of two parts, yc, the complementary function, and yp, the particular integral. Then go on to this steps, that is for yc, we take the equation in its reduced form, which is yt plus 1 plus 3yt is equal to 0. Let the trial solution be yt is equal to ab to the power t, where ab to the power t is not equal to 0. We once again substitute like the previous example and get yc to be a into minus 3 to the power t. For particular integral, we again take yt equal to k as our trial solution and get the value of k to be 1. So general solution is this, a minus 3 to the power t plus 1, and now our y0 was 4. So this gives us the value 3 for a, and we substitute 3 here to get the solution as 3 into minus 3 to the power t plus 1. We will take just this example to show how to solve this. This equation we have to normalize. That is, we have to make this term not have any coefficient. So our equation is 2yt plus 1 minus yt is equal to 6, and initial condition is given by y0 is equal to 7. So our general, again this is a first order linear non-homogeneous difference equation where the general solution is consists of two parts, complementary function yc and particular integral yp. For yc, we take the equation in its reduced form, that is yt plus 1 minus half yt is equal to 0, and proceed with the previous steps in order to get yc equal to a into half to the power t. Now for particular integral, let the trial solution be k. This gives us the value of k to be 6. Now again we put in our initial conditions to get the definite solution as yt is equal to half to the power t plus 6. There is another example which will be solved in the same manner. That is, you take all the terms involving yt on the left hand side and keep just 4 on the right hand side, or the non-zero part without yt on the right hand side, and start the solution, and you solve in this manner and you get a solution like this. I hope it's clear up till here. Is there any question from any one of you? Please respond, otherwise I will not know.
No, ma'am.
Are you still there?
Yes, ma'am, it's clear.
Acha, it's clear?
Yes, ma'am.
Okay, and can you hear me properly?
Yes, ma'am.
Okay, okay. Now we come to the significance of B. What was it? Our trial solution for the equation in the reduced form, that is a complementary function, had a term B, that is A B to the power T. We are now considering the significance of that B. Now, equilibrium is dynamically stable when complementary function tends to 0 as t tends to infinity. Therefore, we must analyze the path of the term a b to the power t, not as t is increased indefinitely. Hence, the value of b is of crucial importance. Now, first we consider its significance alone by assuming A is equal to 1. Since we are not considering, since we are considering period analysis, the graph is a step function rather than a smooth function. That is, there are steps in the graph. Now, for analytical purposes, we divide the range of possible values of B in the range minus infinity to plus infinity into 7 distinct regions. Region 1, we take the value of B to be greater than 1. Any value we can take, that is, we are taking the value of B to be 2 in our example. So, b to the power t will increase with t at an increasing pace. So, when t is equal to 0, 2 to the power t is equal to 1. When t is equal to 1, 2 to the power t is equal to 2. When t is equal to 2, 2 squared is equal to 4. When t is equal to 3, 2 to the power 3 is equal to 8, and this way we move on. So let us come to the figure or the graph. Here we are measuring what? Here we are measuring the time, and here b to the power t. So when t is equal to 0, and the value of b to the power t is 1. Now, when t increases to 2, the value of b becomes 2. So here, so this way we find that the steps, the difference between the steps increase at each level. Okay, I'll take a short break. I'll be back in 2 minutes. What we found was that this distance between these were increasing. as t increases, bt, the differences between the values of bt went on increasing. Now we come to region 2. That is, b is equal to 1, absolute value of b is equal to 1. So, whatever the value of t be, b to the power t will be equal to 1 and will get a horizontal straight line like this. Now we come to region 3, where b lies between 0 and 1. So this is a positive fraction raised to integer power. As the power is increased, b to the power t decreases but always remains positive because b is greater than 0, though less than 1. So it is a positive fraction. So when t is, we are taking it to be half, the value of b is half. So when t is equal to 0, value of b to the power t is equal to 1. Now when t is equal to 1, value of b to the power t is equal to half. When t is equal to 2, the value of b to the power t is equal to 1/4. So this distances between these steps go on decreasing as t increases. Now we come to region 4. Now what does region 4 tell us? Yeah, b is equal to 0. That means absolute value of b is 0. So whatever be the value of t, it will be 0. The graph will coincide with the t-axis. Now, this case is of peripheral importance only, peripheral interest only, since we assume that a b to the power t is not equal to 0. So, b is equal to 0 does not arise in this case. Now we come to region 5. Here it is what? It's greater than -1. The value of b is greater than -1 but less than 0. This means it is a negative fraction such as -half. What will happen? When we have negative sign, the time path becomes oscillatory. That is, in one period it is positive, in the next period it is negative, and it is positive again, and then negative again. It goes on. So in this case, where the value of b is a negative fraction, we have b is equal to -half. So when t is equal to 0, we start again from 1. When t is equal to 1, what happens? -half to the power 1 is -half. So this distance gets halved, but it is below the time axis. Again, when t is equal to 2, we get +1/4. That means it goes above, and this distance becomes half again, and this process goes on. So what do we get? Alternating time path tends closer and closer to the horizontal axis. Why does it become closer to the horizontal axis? Because the absolute value of B is less than 1. Now we come to the sixth region. What is it? B is equal to -1. So absolute value of B is equal to 1. So when t is equal to 0, b to the power t is equal to 1. When t is equal to 1, b to the power t is equal to -1. When t is equal to 2, b to the power t is again 1. When t is 3, b to the power t is again -1. So a perpetual alteration between +1 and -1 is taking place. So we have the last region left, which is it? The region 7, where B is less than -1. So absolute value of B is greater than 1. So we take the example of B is equal to -2. So when t is equal to 0, again, what? B to the power t is equal to 1. Now, when t is equal to 1, b to the power t is equal to -2. When t is equal to 2, b to the power t is equal to +4. So, this distance increases as the t increases. The value of b to the power t increases, but it alternates in sign. So we have a oscillatory time path again, but this will deviate further and further away from the horizontal axis. Hope it's clear up till here. Are you there?
Yes, ma'am.
Okay. So, if we summarize the above discussion, we find that the essence of the preceding discussion can be conveyed in the following way. The time path of BT, where B not equal to 0, is non-oscillatory if B is greater than 0, oscillatory if B is less than 0, divergent if absolute value of B is greater than 1, convergent if the absolute value of B is less than 1. Now we come to the role of A. That is, while discussing the nature of B to the power t, how it affects the time path, we assume that A is equal to 1. Now we remove this assumption and find the role of A. There are two effects that A can have on the time path. First, the magnitude of A can serve to blow up, say if A is equal to 3, or pare down, if A is a fraction, the values of B to the power t. That is, it can produce a scale effect without changing the basic configuration of the time path. 2, the sign of A materially affects the shape of the path, because if B to the power t is multiplied by A equal to -1, then each of the time paths shown above will be replaced by its own mirror image with reference to the horizontal axis. What we obtain above the t-axis will come below it, and vice versa. So we find that A also may have two effects on the time path of Y. Now convergence, a few words about convergence to equilibrium. The complementary function AB to the power t term represents the deviations from some intertemporal level. If the term say yp is equal to 5 is added to AB to the power t term, the time path will be shifted up vertically by constant value of 5. This will in no way affect the convergence or divergence of the time path, but will alter the level with reference to which convergence or divergence is gauged. In the above discussion, we pictured convergence or lack of it of the AB to the power t expression to 0. When yp is included, it becomes a question of the convergence of the time path yt is equal to yc plus yp to the equilibrium level yp. In region 2, p is equal to 1, the time path becomes yt is equal to a1 to the power t plus yp equal to a plus yp. This gives an impression that it converges because the multiplicative term 1 to the power t is equal to 1 produces no explosive effect. However, yt will now take the value a plus yp rather than the equilibrium value yp. In fact, it can never reach yp unless a is equal to 0. As an illustration of this situation, we have, say, yt is equal to a into minus a to the power t plus ct, which gives us a plus ct. So this is a moving equilibrium. Yp is equal to ct. This time path is divergent, not because of the appearance of t in the particular integral, but because with a non-zero a, there will be a constant deviation from the moving equilibrium. Thus, in stipulating the condition of convergence of time path yt to the equilibrium yp, we must rule out the case b is equal to 1. In sum, the solution yt is equal to ab to the power t plus yp is convergent path if and only if the absolute value of b is less than 1. Let us take one or two examples. That is, what kind of time path is represented by yt to minus 4 by 5t plus 9. b is equal to minus 4 by 5, which is less than 0. That means it will give us an oscillatory time path. Now the absolute value of b is equal to 4/5, which is less than 1. So the oscillation will be damped. Therefore, the time path will converge to the equilibrium level. A word of caution can be put here is that this 2 minus 4 by 5 to the power t is totally different from minus 2 4 by 5 t. They represent extremely different time paths. Configurations, because this will give you oscillatory time paths, whereas this will not. We take another example, that is yt is equal to 3, 2 to the power t plus 4. Here 2 is greater than 0, implies there will be no oscillation, but absolute value of B is 2, which is greater than 1, time path will diverge away from the equilibrium level of 4. It's clear up till here? Any
Yes,
questions?
ma'am.
Any questions?
No, ma'am, it's clear.
Okay. So now we move on to the model we were supposed to do in case of first order difference equation, which is cobweb model. I will give you a represent the model with a single diagram. There can be two other possibilities of the cobweb diagram. You try it on your own and send it to me, and I will check it for you. So here, I hope everyone knows what is a cobweb, that makosha jalke cobweb bola hoy, shobai jani amra. So consider the agricultural production. Now, planting must precede the harvesting and sale of output by an appreciable length of time. That is, we have a situation in which the producer's output decision must be made one period in advance of actual sales. Let us assume that the output decision in period T is based on the prevailing price PT. This output will not be available for sale till period T plus 1. Thus, PT will not determine the supply QST, but QST1. Therefore, we have a lagged supply function, that is QS T plus 1 is equal to SPT. The price in the period T determines the supply of period T plus 1. Or we can write QST is equal to SPT minus 1. We can write like this, as you have seen in the beginning of trying to solve this differential equation. Here we are making the implicit assumption that the entire output of a period will be placed on the market with no part of it held in storage. Such an assumption is appropriate when the commodity in question is perishable or when no inventory is kept. That is, the entire output is brought to the market for sale. Now, the demand curve is given by QDT is equal to the function of PT. When such demand and supply functions intersect, interesting price patterns result. That is cobwebs result. We will try to understand how these cobwebs arise. Taking the linear versions of these lagged supply and unlagged demand function and assuming that in each period, each time period, the market price is always at a level which clears the market. We have a market model with the following three equations. We all know that quantity demanded is equal to quantity supplied at equilibrium. Now, quantity demanded is alpha minus beta PT because we are assuming beta to be positive. So, we put in a negative sign to indicate the negative slope of the demand curve. Likewise, we have quantity supplied is equal to minus gamma plus delta. Delta is the slope of the supply curve, which is a positive slope, but this quantity supply depends on the price of the previous period. By substituting the second and third equation, in the first we get a difference equation of the type beta pt plus delta pt minus 1 is equal to alpha plus gamma. So we know beta to be the slope of the, rather the negative value of the slope of the demand function, and delta the slope of the supply function. This is a first order linear non-homogeneous difference equation. Whichever difference equation you solve, the first line you have to write is this, the nature of the difference equation. This is a first order linear non-homogeneous difference equation in this case. In order to solve this equation, we normalize it by shifting ahead the time subscripts by one period. That is P T plus 1 plus delta by beta pt is equal to alpha plus gamma by beta. This pt term should have no coefficient, so we have divided the entire equation by beta to get this equation. Let the time path be pt is equal to alpha plus gamma by beta. Sorry, the difference equation be that. Sorry, I totally misquoted the last sentence. Our difference equation is P t plus 1 plus delta by beta into pt equal to alpha plus gamma by beta. Then we start solving the equation and say that let the time path be pt equal to pc, the complementary function, and pp, the particular integral for the complementary function pc. We take the equation in its reduced form. So we take pt plus 1 plus delta by beta pt is equal to 0. So pc is equal to a b to the power t, where a b to the power t is not equal to 0. We substitute for y's in with a b to the power t to obtain the value of b as minus delta by beta, since a b to the power t is not equal to 0. So our particular complementary function becomes pc is equal to a minus delta by beta to the power t. For particular integral, let the trial solution be pp equal to k. Substituting k for in the entire difference equation, we get the value of the particular integral as alpha plus gamma by beta plus delta. By adding the complementary function and particular integral, we have the general solution as pt is equal to a minus delta by beta t plus alpha plus gamma beta plus delta. To definitize the solution, we put the initial conditions. Let the initial conditions be P0. So P0 is equal to A plus alpha plus gamma over beta plus delta, which gives us the value of A as P0 minus alpha plus gamma over beta plus delta. We substitute the value of P in our general solution to get the definite solution of this nature. Here we observe 3 points regarding the time part. One, the particular integral Pp is equal to alpha plus gamma over beta plus delta. This is the equilibrium price of the model and we refer to this as P bar. So particular integral is our equilibrium price of the model and so we can substitute this value with P bar because we always write the equilibrium price as P bar. So P bar is equal to alpha plus gamma over beta plus delta. Now as far as the market clearing sense of equilibrium is concerned, the price reached in each period is an equilibrium price because we have assumed that quantity demanded is equal to quantity supplied for every period. So, as far as the market clearing sense of equilibrium is concerned, the price reached in each period is an equilibrium price. Since this is a constant, it is a stationary equilibrium. Substituting P bar into our definite solution obtained previously, we get a much simpler looking solution as Pt is equal to P0 minus P bar into minus delta by beta to the power T plus P bar. Now we come to the significance of this P0 minus P bar. What does it mean? Its sign will bear on the question of whether the time path will commence above or below the equilibrium. That is, whether the time path is above the equilibrium, begins above the equilibrium, or begins from below the equilibrium. Its magnitude will decide how far away or below it is of the equilibrium. So that is our scale effect. Now the third component. What is the third component? Third component is minus delta by beta. From our model specification, we know that beta is the slope of demand and delta is the slope of supply. And beta and delta are both greater than 0. We deduce an oscillatory time path because we have here the minus sign. So time path will be oscillatory. There can be 3 possible varieties of oscillation patterns in this model. The oscillation will be explosive, which I'll show you just now. It may be uniform or it may be damped. It is explosive when delta is greater than beta. It's uniform when delta is equal to beta. It is damped when delta is less than beta. So, explosive implies it moves away from equilibrium. Uniform means it just moves around the equilibrium, and damped means it moves towards the equilibrium. Now we have a downward sloping linear demand curve with its slope numerically equal to beta. We also have a linear supply curve with slope equal to delta when we let the q-axis represent a lagged quantity supplied. The intersection of demand and supply will yield a intertemporal equilibrium P bar. When delta is greater than beta, that is, we have a steeper supply curve. We get an diagram like this. Demand curve is this. The supply curve is steeper. We get an equilibrium P bar. Now our P0 is greater than P bar, initial condition. So what do we have in the initial condition? We have here what? Here demand is this much, supply is greater, demand is greater than supply. So we move here and at that quantity of demand, the price of supply is this. So we have a cobweb of this type which is moving away from the equilibrium price P bar. We are moving away from the equilibrium. We had started from here, we have moved here, then there, then there, then here, then there, then there. Like this, we are moving away from the equilibrium price. So this is an explosive oscillation since delta, that is slope of supply, is greater than demand. We would have had damped oscillations if slope of demand was greater than supply. And if we have a slope of demand equal to supply, we will have a cobweb like this going around the equilibrium like this. Now let's just talk in detail about this. When delta is greater than beta, the interaction of demand and supply will produce an explosive oscillation. Given an initial price of P0, here assumed above P bar, we can follow the arrowhead and read off the supply on the supply curve that the quantity supplied in the next period, that is period 1, will be Q1. In order to clear the market, quantity demanded in period 1 must also be Q1. This is possible if and only if price is set at the level of P1. Now, via the supply curve, the price P1 will lead to Q2 as the quantity, and this process will go on repeating this reasoning. We trace out the prices and quantities in subsequent periods by simply following the arrowheads in the diagram and thereby spinning a cobweb around the demand and supply curve. Now, I will give you as an assignment to draw the diagrams for the case when we have damped oscillation, that is the slope of demand is greater than the slope of the supply, that is the absolute value of slope of demand is greater than absolute value of supply, the slope of supply, and when the slopes are equal. This I will put you as an assignment to you and expect to get it by today. I hope it's clear up till here.
Ma'am, can you repeat the assignment?
Please respond.
Ma'am?
Yes, you have
Hello?
any questions?
Yes, ma'am, can you repeat the assignment?
That is, I have shown you what happens when the slope of supply is greater than the slope of demand. We get explosive oscillations. Now, when the absolute value of demand is greater than the slope of supply, then we will have damped oscillation. So you draw that diagram. You draw the demand curve steeper than the supply curve. Then you'll get damped oscillations, and the case where slope of demand and supply are equal, then you will get uniform oscillations. That also you draw. That's your assignment.